To understand how your brain instantly knows the difference between a feather brushing your arm and a hot stove burning your hand, we have to look at the physiological evidence. We are going to deconstruct the actual mechanisms laid out in Guyton and Hall's medical physiology text to see exactly how these sensory signals are routed. Every sensation begins with specialized receptors in the skin. One of the most sensitive is the igodome receptor, driven by structures called Merkel's discs. Inside this microscopic dome, multiple disc-shaped receptors connect to a single nerve fiber, registering touch with extreme precision. Whether it's a light touch or sharp pain, all sensory signals follow the exact same road, entering through the dorsal roots at the back of the spinal cord. Once inside the spinal cord, however, their paths diverge. The signal is immediately sorted onto one of two separate neural highways, based entirely on the specific type of information it needs to deliver. For high-fidelity signals like discrete touch, vibration, and joint position, the nervous system uses the dorsal column medial lemniscus system. These signals travel up large, myelinated fibers at speeds of up to 110 meters per second. Notice that the signal travels straight up the back of the spinal cord, on the exact same side it entered. A common mistake is thinking all nerves cross over immediately. They don't. The signal stays on its original side all the way up the spinal cord. Only after synapsing in the medulla does it cross the midline and continue up to the brain. The journey ends in the somatosensory cortex. Here, the body isn't mapped by physical size, but by receptor density. Areas requiring fine sensory discrimination, like the lips and the fingertips, command massive amounts of cortical processing space. This graph shows the raw, unedited signal from two adjacent pressure points on the skin. Without processing, it registers in the brain as a single, broad, blurry zone of excitation. To make sense of that data, the brain applies side pressure. The excited neurons send out inhibitory signals to their immediate neighbors. This lateral inhibition blocks the diffuse background noise, transforming that single blob into two distinct peaks of excitation. Without this active sharpening mechanism, your brain couldn't distinguish 2 points of pressure from one. You would be unable to read Braille, judge the texture of a fabric, or perform any task requiring fine manual dexterity. Now let's trace the second route, the anterolateral system. This is a slower pathway designed to transmit pain, temperature, and crude touch. The wiring here is completely different. The moment an alarm signal enters the dorsal horn of the spinal cord, it synapses and immediately crosses over to the opposite side, before traveling up toward the brain. This specific wiring architecture explains one of the most vital clinical phenomena in medicine, referred pain. This is when deep visceral damage, like a heart attack, is felt on the surface of the body. We can trace this to a literal intersection of nerves. Visceral pain fibers from the heart and somatic pain fibers from the skin of the left arm frequently synapse on the exact same second-order neurons inside the spinal cord. When those shared neurons send a distress signal up to the cortex, the brain has to interpret the source. Since the brain has no conscious, daily experience of the heart, it defaults to the most common source of pain input, the exterior skin. The sensation in the arm is entirely real to the patient, even though the arm is perfectly healthy. Referred pain is simply the brain making its best geographical guess for an internal crisis, based on its own surface map. These pathways are functionally separate. This chart plots nerve discharge against skin temperature. As temperature drops, cold receptor firing increases, peaking at 24 degrees Celsius. But at extremes, below 10 or above 45 degrees, standard thermal receptors shut down. Instantly, dedicated pain fibers take over. Because these pain and temperature pathways are mapped to highly specific segments of the skin, called dermatomes, physicians can pinpoint the exact height of a spinal cord injury simply by testing where a patient loses the ability to feel a pinprick or a cold compress. This crossover is why touching dry ice and a hot iron yield the exact same sensation. The feeling of burning cold occurs when an extreme stimulus abandons the thermal receptors entirely and hijacks the primary pain highway of the anterolateral system. When you feel a stimulus, remember its route. To precisely identify an object by touch, the signal stays on the same side, racing up the dorsal column. If it causes pain, it immediately crosses over, sounding the alarm.